So what we're going to do today is just some review on integrals. At the end of the period, we'll start some new stuff. Surface integrals are not included on the final, but I will still do them. Well, surface area, a particular type of surface area is not included in the final. We will just see how to do this. Then tomorrow's material will be totally new stuff. Okay? So, which is included in the final. Of course, you're not going to have something very intensive on it. I'll leave it to your judgment to see how to study these things like that tomorrow, but do not expect very tough questions on tomorrow's lecture. Actually, it's going to be more or less very straightforward. Okay, so now we'll just do some review on triple integrals. I will try to mix things up. I will do some hard problems. I'll do some easy problems, but the level is the level that you should be expecting on Tuesday. Okay? So you should expect this level on Tuesday. Great. Let's get started. So we'll start with spherical coordinates, let's say, or I think I'll just use the problem and then you can tell me how to approach it. Okay guys, let's get started. Where R is the region bounded between the sphere. Okay? We'll see now that maybe we can set up our problem in many different ways, but what we'll see is that one way may be easier than the other. Okay, that one way may be easier than another way. So let's try this problem. First of all, how to approach it? What's the first thing to do? I have a thing in 3D. What can I do? I can do a rough sketch of the region of integrating over. How do I sketch that? How do I sketch the sphere of radius 1? Right? And then I have a cone. Z is equal to square root of x squared plus y squared. Now we've seen that the angle that the cone makes with the z axis is constant. The cone makes and is equal to pi over 4, and so we're really integrating over this region, over this solid inside. How do I approach this? What's a good way to approach this? Everybody, do we agree with the region? Yeah? We agree with the region we're integrating over? Great. How to approach this? We have many ways. Yes, sir.
I just have a question.
Yeah.
How did you envision, how are you able to draw that?
The cone?
Yeah.
The cone. So what is the cone in spherical coordinates? You remember, it's phi. This cone is phi equals pi over 4. Right? So your angle with the vertical is pi over 4. And you just do it. Okay? Yeah. Pardon me? So we saw in Persian coordinates, we called that the angle with the z-axis, this angle, phi, right? Remember? And it ranges from 0 to pi. Now, if you solve this in terms of spherical coordinates, you will find that cos phi is equal to sine phi. This means that phi is equal to pi over 4 since phi is between 0 and pi. So really this angle is constant and you're just turning. Okay? Is it clear? Great. So how to, yes?
If you get another equation for the cone, you have to solve it.
Yeah, you can solve it. So we can do another one. Should you try another one? Let's see if we can do another one. I mean, we can put a C, but we can put a C here, right? Sure, we can put a C. Maybe a bit more complicated. Well, I mean, it's not. Let's keep it this way. Okay, let's keep it this way. Okay, we're really starting this. Let's keep it this way. It's not bad. You just solve it. So you get cos phi is C times sine phi. You know that cos squared plus sine squared is equal to 1. So you'll just solve for cos phi. Cos phi may be like C over square root C squared plus 1 if C is positive. And phi will just be, since C is positive, so phi will be arc cos of C over square root C squared plus 1. Now if C is equal to 1, phi will be arc cos of 1 over root 2, which is 5. Okay? Just try to do it and put a C, a positive constant. Okay? You'll be able to solve it. Great. How to approach this problem? What's one way to approach it? Sure. They intersect the disk. You agree that these two intersect the disk? So what approach are we taking? So we're just trying to bound Z, right? And then projecting the intersection onto the xy plane, right? That's what we're trying to do. So let's do this. What is Z on top here? I mean, I'm interested in what values of Z are Z is negative or positive in my region. In R, Z is positive. So to find this intersection here, how do I do this? I equate the two equations, right? So what is that? This is let's see. So I'm just wondering if I write it down. So I mean, Z squared is 1 x squared plus y squared, and Z squared is x squared plus y squared, right? This is what you're doing. Right? So what do you get? You get x squared plus y squared is equal to what? What is that? So x squared plus y squared is equal to 1/2. And what is the value of z? Z squared is 1 minus 1/2. So z is equal to 1 over root 2. Okay, so this is the curve of intersection here. Now when I project this curve of intersection onto the xy plane, I have a circle here, I project it. I get a circle in the xy plane. The circle x squared plus y squared is equal to 1/2 in the xy plane. And over what region I'm integrating? Over the the xy plane. So in this region, the sphere is bigger than the cone, right? You see that? So I'm integrating. And where does Z range? Z ranges from where to where? From the cone to the sphere. Everybody, we agree? We see that? Yes or no? Z ranges from the cone to the sphere. I want the volume, so I integrate 1 dx dy. Great. Now, are these nice integrals to evaluate? We switch to polar or to cylindrical, right? You see this? Oh, shoot. Thank you. Yeah. Thanks. Yeah, otherwise, yeah, thank you very much. Yeah. Now, what do I do here? I have x squared plus y squared. I eliminated all my z's. So what do I get? is constant. X and Y are constant with respect to Z. Right? What is that here? It's good. Just a second. This is fine. Yep. Great. Now, how do I evaluate this integral? I know how to evaluate. It's a double integral, right? Do I know how to evaluate it? It's just plus here, not minus. Do I know how to evaluate this integral? I switch to polar, right? So it's a double integral. So x is r cos theta, y is equal to r sin theta. R varies from where to where? 0 to 1 over square root 2. Theta varies from 0 to 2 pi, right? X squared plus y squared, what does it become? You want to say something? Yeah? No? Okay. Times square root of 1 minus r squared, right? Oh man, it's gonna get bad. Minus r, then what? dx dy, what does it become in terms of dr d theta? R dr d theta. It's gonna get bad. You see why it's bad? Yes, sir. Yeah. No, 2 pi. Here, 2 pi. Okay. Great. Now you guys know how to integrate this. You have r cubed. Oh my God. Okay, no, that's still not bad. That's still not bad. What is that here? So I am integrating over a rectangle in r and theta, right? And I'm integrating a. Is this good? Are you guys doing it? This is fine? Yeah. Yes.
I wonder why that was square root of x squared plus y squared.
Sure. Cool. Do you agree that z goes from here to here? Okay. Yes. What is that?
From the circle.
From the cone to the here. What is the equation of this stuff of this here? And what is the equation of this cone? Okay, now it's going to get ugly, but that's fine. We can do this. We can do this. We can do that. Let's see how to do this. Man, okay. So what do I get? You agree that I can take a 2 pi out, right? Because it's a product of two functions. One of theta, which is 1, times a function of r over a rectangle. And then I have to integrate from 0 to 1 over root 2, r cubed square root of 1 minus r squared dr. I think you can do this one many ways. Plus I have minus the integral from 0 to 1 over root 2 r squared dr. Right? Are we following? So that you can do it in many ways. You can do it by parts, or you can do it by u sub. Maybe u sub. Let's try u sub. I think it's the first time I'm running a u sub here. du, what is du? It's 2r. dr, so you get square root of 1 minus u. Square root of 1 minus u. Yeah, I mean, it doesn't help, right? It doesn't really help. Right? Does it help? Do you see that it doesn't help? I mean, you still have to do it by parts. So, it doesn't really help. So let's do it here. It's 2 pi. 0, 1 over root 2. Okay, so let's do this. Should we do this in a nice way? I'll write this R. Minus, let's write this on here. Yes, sir. Oh shoot, R square R4, yeah, thank you. So 5 over 5, is that right? Is that what you have? Thank you. Great. Now how do we integrate this? We can integrate this by parts, right? This is u prime, and this is v. So let's do an integral here. And then the derivative of r squared. dr. What is that? This is just r squared. What's the next derivative of this one? This is just 1 minus r squared. The 3 halves. Times minus 2 times 3 halves. From r is equal to 1 over root 2 to 0. Minus the integral. So u v prime. So it's u v minus v prime u minus the integral of v prime. What's v prime? Is 2r. What is u? Right? You guys see this? This is good? This is good? Yeah? Are we good here? By parts? Are we good? Integral of u v prime is u v minus integral of v prime u. Right? Great, let me evaluate this thing. Now this is easy to integrate, right? You see that's easy to integrate. So r squared, blah blah blah, 1 over root 2, what do I get? I get 1 half times 1 half to the 3 halves, right? 1 half to the 3 halves. Over minus 3 plus 0, right? Then let's integrate this one from 0 to 1 over root 2. What do I get here? I get 1 minus r squared to the 5 halves over 5 halves minus 3 here. Right? Is that what I have? Yeah, that's right. 5 halves, 5 halves. 2 is good. So what do I get here? So I get 1 half over minus 3 plus 1 half to the 5 halves times 3/5 over minus 3 plus 1 plus 2/5 plus 2/5 over 3. Is that it? Do we get this or not? Yes? Did we get that? I could have easily messed it up. So I mean, we're integrating a positive function, so the answer has got to be positive. So you get 1 half over 3 minus, so 2 over, so you get minus 1 over 4, right? Over 3, right? 2 to the 5 halves multiplied by 2, so you get 2 to the 3 halves. Plus Is that what you get? I think, yeah, is that what you get? Do you guys get this? Do you guys get this or not? Is there a mistake somewhere?
I mean, I might have, but I made like a 3, power of 3 over 2 on the first term.
On the first term?
The first one. The
You
one
got
that's
this?
like negative 1/2 over 3. The other one on the left.
Here, you have a 3 over 2.
Yeah.
3 over 2
Oh, but
should be
you
1
guys
over,
don't
no, you're right. No,
Unless
it's
you
1
guys
half squared.
1/2.
Right, it's 1 half squared. Right? 1
Yeah,
half times
you
1
guys
half.
did that, yeah.
No, it's 1 half to 5 over 2. Oh god. Okay, that makes it nicer.
That was
So what do you get? You get minus 3. And you see that this is that what you get? Yeah. Okay, great. 1 half times 1 half to 3 halves. Yeah, that's 1 half to 5 halves. 1 half to 5 halves. Great. I mean, you know, this looks. Yes. Where? Here? The first word?
No, all the way
Up. Up.
like next to it.
Yeah?
Yeah, this one.
Oh, plus? Did I put a minus? Is there a minus somewhere?
Like if from the integration by part, it would be a minus.
From the integration by part, it's a minus. Right. Well, the minus. Okay, guys, this is good. The first one is good. Then I integrate this one. 2r. How did I integrate this one? So 1 minus r squared, the derivative of this one. I have a minus 3 down. Right? You have a minus here. Now once you take the derivative of 2r squared, right? Try to differentiate this one. Yeah, I think it's 1 minus 2r, right? Minus 2r.
And then,
Okay. Is that correct? Okay, did you guys have this? So what is my final answer here? This is 2 pi. Times this whole thing, but let's double check that it's good actually. I'm worried that it's not good. So 1 half. Yeah, no, I think it's good, right? It's good. Anyway, so you get this minus. Okay? You get this whole business here. Call this A. Now you see sometimes that the choice of coordinates matters. You see that? I did this problem in cylindrical coordinates, and it was a lot of work, wasn't it? Did you get the same answer? Did we get the same answers for those who tried it? Yes, sir. Here? This one? You have a minus here. So 1 half to the 5 halves. You agree with this? Oh, here, yeah. Oh god, okay. Yeah, so minus here. Oh, yeah. Did we try it or not? Okay, try it. Yes, sir. Yes. guys, please, in the back, please. X squared plus y squared is equal to 1/2, right? This is the region where x and y are very close. Okay? The radius in the xy plane goes from 0 to the square root of that number. What's the square root of that number? Okay, great. Now let's try it in spherical coordinates. In spherical coordinates, this may be easier. Of course, you should get the same answer in both cases. This was a pain in the neck to do. Was it? Yeah, I think it was. Yeah, I think it was a big pain in the neck to do. Now I count on you. You guys get the same answer? Yeah, for those who tried, did you get the same answer? Okay, great. So let's try to do it in spherical coordinates. In spherical coordinates, the region may be easier to describe. So I have to integrate over this region. So really, theta will go from 0 to phi. Phi, where will phi go? Phi will go on the cone z is equal to square root of x squared plus y squared. So I have that z is rho cos phi is equal to rho sin phi. So cos phi will be equal to sin phi. And phi will be equal to pi over 4. So I'm inside the cone. So phi, will it exceed pi over 4? So phi will go from 0 to pi over 4. And rho, when will rho vary? 0 to 1. Great. Now what is x squared plus y squared in terms of spherical coordinates? It's just rho squared, sine squared, phi. Rho squared. So it's, what is that? So it's rho x sine phi cos theta, right? And y is rho sine phi sine theta, right? When I square these two things, what do I get? When I square them and add them together, I get rho squared sine squared phi, right? So let's do that here. What do I have not to forget? The Jacobian. What is it? It's rho squared sine phi d rho d phi d theta. So I have a 2 pi. And then I have a 1 over 5 rho to the 4th, so it's, and then I have, let's see. Now if you had done a trig sub here, had you done a trig sub, you would have gotten this integral, I think. Okay? I think, maybe. Who knows? But I think so. Because this, yeah. Had you done a trig sub somewhere, you may have gotten this. So let's do this. What do I get? I get 2 pi over 5. And how do I integrate sine cube? Sine squared times sine. So it's 1 minus cos squared times sine, right? So it's 1 5. So you get 2 pi over 5. Let's see. So we integrate sine phi from 0 to pi over 4. So it's minus cos phi from pi over 4 to 0. And this is minus root 2 over 2 plus 1. Now we have to integrate u squared times u prime. So you have to integrate cos squared phi sine phi to phi. You still get that? And then how do you integrate that? You can do a u sub. U is cos phi, right? du is sine phi minus sine phi to phi. So here what do you get? You get it's cos cubed over 3, right? So you get 2 pi over 5 times 1 minus root 2 over 2. Cos cubed 3 cos squared minus sine phi. That's it. Cos cube of this is 1 over root 2 cubed plus 1 over 3. Okay, what is easier, this one or the other one? This one, although this one is not very nice, but it's still easier than the other one. Okay? Yes? So how many lines depends on your handwriting. But in my handwriting, I could fill all the answers on the, so you have a multiple choice, A, B, C, D, right? Well, I mean, when I try that, it's A, B, C, D, E, and I could fill my answers on the multiple choice. On the same, I could fill my long answers. But again, that's me. I have write very small, like very, very small, okay? So, yeah. Okay, now a quick exercise to try to show that these two are yeah, I mean, they look really ugly, huh? Great. You see, one way can make it easier. Should we do another one? Should we do another one? Let's say another an easy one, where you may have to do a substitution, for example. Yeah. So I've been asked a lot about trig subs. We'll do one example with a trig sub, okay? Or you could do it with a trig sub. Let's try to do one. It's an easy question. And we're just doing review now. I'll keep on doing. Today will just be review. I will not try anything here. Fine. Okay. So we have an integral. Find an integral. Does this look good? Can you integrate square root 1 to the minus 4? Can you find a closed form for this an antiderivative for this function? No. So what's the second step? We immediately sketch the region of integration, and perhaps I can try to switch the order of the integrals, right? I don't think it will work here. I don't think a change in u, in x and u, in x and y. Yeah, but what is your? I don't think may work, but I cannot tell from the beginning that it's gonna work. So let's try to sketch the variables. What are the curves that I have? Y is equal to x. This is easy. And y is equal to x to the 1/3. And y is equal to x to the 1/3, or something like that, right? And of course, x is between 0 and 1. These intersect at 1, 0, and this is 1. So where is my region of integration? Is it this one, or this one? Or this one? Middle? The middle, right? Great. Here I have y expressed between two functions of x and x between two constants. What do I need here? I need to express what? X between two functions of y and y between two constants. What are my two constants for y? Obviously 0 and 1. Very good. Y varies from 0 to 1. And what are my bounds for x? So y, where will y go? Where will x go? X will go from this curve to this curve, right? What is, so this is y is equal to x to the 1/3. What is x in terms of y? y cubed, right? So x will go from y cubed to y. Of course, this is easy. Square root of 1 minus y to the 4 dx dy. Now at least I can do something. So 0 to 1. Y square root of 1 minus 4 dy minus, right? It's minus 0 to 1 y cubed square root. This is easy, right? The derivative of y to the 4th is 4y cubed, so that's good. I can integrate that easily. Here it's a bit hard. Well, not very hard, but so let's keep the first one on the side. I mean, really, let's see if we actually need a trick sum, or we can try to do without. Now the second one, we just minus 1 to the 4 to the 3 halves divided by 3 halves, and then I have to multiply by 4 and have a minus 4, I guess. So what do? I have a plus from y is equal to 1 to y is equal to 0. Let's see what I get. So minus y is equal to 1, this becomes 0, and then I get minus 1 over 4 times 3 over 2, this is minus 1 over 6. Is that good so far? Are we here? So are we good? Yeah? Then I have to integrate the other one. So what change of variables do you suggest to do? Or you want to cancel the u du, right? How can you cancel the u du? You said, well, you want to cancel the y dy with something nice. What's a good way to cancel the y dy?
I have a question about the three.
Yeah.
You chose 5 from 0 to pi over 4.
Yeah.
Remember? Why didn't you choose it from pi over 4 to 3 pi over 4? The cone was going like this, you know?
No, the cone, I'm inside the cone, right?
Yeah.
Right?
Okay. I thought you were going like from the x-axis.
No, like the cone is inside, so you're going this way, right? Okay? Yeah. Great. So how do I integrate that? What's one sum to get rid of y dy while still being interesting and easy to me? U is equal to y squared. So if u is equal to y squared, u is equal to y squared. If y is equal to 0, so u is increasing as a function of y in 0, 1. If y is equal to 0, what is u? 0. And if y is equal to 1, what is u? 1. dy will become, y dy will become du over 2. And here I'll have square root of 1 minus y squared. Great. Now how do you evaluate this integral? How do you evaluate this integral? Let's try to avoid a trick sum. Let's try to avoid a trick sum. You can do a trick sum. Do you want to do a trick sum? Yes, sir.
Since I haven't done much tricks on, do you think we can't do any hammer now?
Calc 2 is a prerequisite for this course, right? So in case you're stuck here, what are you going to do? You're going to do a trick sum. But how? Is there a way to avoid the trick sum here? Is there a way to avoid it or not? This is a quarter of a circle. Square root of 1 minus u squared is a quarter of a circle, you agree? So what is this is the area under this quarter of a circle. What is this area? Pi over 4 divided by 2 is pi over 8. Okay? So pay attention to these things. Is this clear? You agree that this is the graph of this one. This is root of 1 minus u squared. Right?
Why is this constant?
From 0 to 1. Sure. Sure. Let's try the half circle. Minus 1, right? You want to integrate from 0 to 1? It's this area. What is this area? Pi over 4. You divide by 2. Did you get this? Did you all get this? Did you try this or not? Did you get this? So this is a question you can get. You can get something like that very easy. Nice multiple choice question. Okay? Great. Let's do some more. All good? Where is it? Here. Sure. You agree that this is the quarter of a circle, right? From 0 to 1. Now the integral from 0 to 1 of square root of 1 minus u squared du is the area under this quarter of a circle. What is the area of a quarter of a circle of radius 1? 5 over 4. You divide by 2. 5 over 8. Yeah? Yes? Plus 1 over 6 could be. Could be. Could be. Did we get plus? Anybody get plus? Let's try it. So y minus y cubed. Okay, so differentiate this one. What do you get? You get minus 4y cubed times 3. You get 0. And then you have a minus. Minus square. Sure. Okay, so let me put a plus here and put a minus here. Is that fine? Can I do that? You agree? Okay. Take an antiderivative, differentiate this one. The 3 halves will cancel, right? You will drop a 1/2 to the 1/2, so you get this term, the root. Now differentiate the side. What do you get? Minus 4y cubed. Divide by 4. Minus y cubed. Okay? Great. So things like that you're responsible for. You know, like it's you don't need no tricks up for this. Great. Let's do more. Let's see what we get. Let's do some change of variables. Reverse the rectangle in close by. Okay. Yes, sir. Yes.
Is it not minus 1 over 8? Or
Where?
when you plug in on the left.
On the left?
When you look at y for 1 and y for 0.
Why? Where is that?
The balance, there's 1 minus y to the power of 4 over 4 to the power of 3 over 2.
Where, here?
No. Oh, is it times 3 over 2?
Times 2 over 2 here. You mean here, this one over 6?
Yeah.
This is 6.
I thought it was to the power of 3.
Oh, no. Okay. No problem. Okay, great. Let's do this question. First of all, what do I do here? I mean, on an exam, I will give you the change of variable. I'll tell you what to look for. But in that case, it's obvious. What should I do here? I should first of all sketch. So y is equal to x, right? And then y is equal to 2 minus x, right? Y is equal to x minus 2. Those two lines are parallel. Then y is equal to minus x. And then y is equal to 3 minus x. Well, that's not fair. This is the region I'm integrating. Draw these two lines. Draw these lines. 1, 2, 3, 4. So this is 3. This is 4. This is 2. And this is 1. Right? Do we get the sketch? Well, then let me write for it. Great. Now there's a change of variables that's immediately looking at you. What is u and what is v? U is x minus y and v is x plus y. So let u be x minus y and let v be x plus y. Great. Where does u range? X minus y. U will range from 0 to 2. And v will range from 0 to 3. Great. So integral of r x plus y e minus x squared y squared dx dy. What is that? So u will range from 0 to 2. V will range from 0 to 3. X plus y is equal to what? To v, right? X plus y is equal to v, yeah. X squared plus y squared, what is that equal to? How can you find x squared plus y squared? What I do is solve for x and y, right? And then square them. Or you can square u squared, what is u squared? U squared is x squared plus y squared minus 2xy. V squared is x squared plus y squared plus 2xy. Add them up. You get that x squared plus y squared is u squared plus v squared over 2. Great. So let's see what we get here. You just see that I picked the right function. I picked the wrong function. I knew it was wrong, right? It's x squared minus y squared. Okay, now that's way better actually. That's way better. Because x squared plus y squared you won't be able to integrate it. Great. Sorry about this. What is x? That's easier even. What's x squared minus y squared? U times v, right? That's easy to integrate. I have here v is between 0 and 3. V is x plus y, right? dv and du. Am I good or I missed something? What did I miss? The Jacobian. How did I find the Jacobian? So it's the Jacobian of del x del xy over del uv. You could do that. How do you find this? You could express x in terms of u and v, right? And express y in terms of u and v and find this directly. What's another way of doing this? I take the inverse, right? I know that del xy del uv is the inverse, the reciprocal, like 1 over. I mean, this is determinant. I wrote it this way because it works for determinants and matrices. But the Jacobian here, we're considering a Jacobian determinant. So what is del u del x? Del u del x is 1. Del u del x is 1. Del v del x is 1. Del u del y is minus 1. Del v del y is 1. Inverse. What is this determinant? It's 1 plus 2. So this is 2 to the power minus 1. So it's 1 over 2. So I have here dv du. I suggest that you switch the order of integration just to avoid integrating by parts. Maybe you still have to integrate by parts at the end, but yeah, I mean let's try and do it. So 0 to, so let's integrate with respect to u first. VE of u dv. Okay. 1/2 du dv. Great. What's this integral? With respect to u, v is a constant. So what is this? This is just integral from 0 to 3. This is just e u v from u is equal to 2 dv. So you get 1/2 integral from 0 to 3 e of 2v minus 1 dv. What do you get? 1/2. So you get e to the 2v over 2. So that's e to the 6 over 2 minus 1 over 2 minus 2. Is that what you get? Yes? Did we get this? Did we get this? Everybody, did you try this? Great. Okay? You can expect things of this level. This is not very hard. You can expect also harder. Yes?
I want to know you went from u squared plus g squared over 2.
No. This is just x squared minus y squared. It's not minus x squared minus y squared. Okay, I changed it. Okay? Otherwise, I knew it doesn't integrate. You cannot find a closed form. Yes, sir? Where?
Top right.
Top right?
Top right. Top left.
Here? dv. Okay? Great. Let's do some more. Look at your examples from the book. Okay, are we good here? Are we good? Yeah? Yes, sir. Yes, I'll tell you u is equal v is equal to x plus y and u is equal to x1. I'll tell you. Yeah, but I mean, unless it's a linear change of variable, unless it's u is equal to 3x and v is equal to 2y, for example, you'll have to find this on your own. Okay? Yes, sir.
So a question of this difficulty, would we
as I said,
We would have to.
except a purely linear change of variables, in such a, I will give you the change of variables. But that doesn't make it way easy, right? Doesn't make it way easier. But I just give you the change of variables, so, you know, I think I will put some practice problems. In one of them, it's actually hard. I give you the change of variable, it's a bit hard. Okay? Great. Let's do some examples. But I mean, so the way I advise you to revise for this exam or to review for it, just go through the notes. Make sure you know how to do the examples. Okay, go through the notes. Make sure you know how to do the examples. If you're comfortable with the examples, you get them right, then you should not. It's a good sign, I guess. Yes, sir.
You say you were going to release some homework for practice questions.
Yes.
Is that
Yeah. Okay, but I don't know. Should I put it for grades or not for grades? You don't want this for grades?
No.
Okay, so we'll see. Okay, then, I mean, you know. Great, so I'll see how to do it, you know, without counting for anything. Because, you know, it's going to be a bit painful to remove the grades. Yes? Oh. So I can do a quiz 5, that's going to be optional. You can still hand it in and replace the lowest quiz. I can try and do that. Is that fine with everybody? So it can replace your lowest quiz. Yep. But it's going to be hard. It's not going to be easy, okay? It's going to be like, more like nice questions. Find the volume. Okay, now this is a nice one. Of the solid R enclosed by the surfaces I mean, but I can tell you that this class is a good class. Like, it's a very good class. With the average that you guys have, and the median is very high. So it's median means like half the class, but more than this. So the median is, I said what the median was? Yeah, 88%, which is a very, very high median. So it's good, and I expect many people to do. And for an exam that was not very easy, I wouldn't say it was very easy. I mean, the series that were there, say you got them in class 2, I think would have been a bit hard. But anyways, you guys practiced well, you did well. So on the final, I expect the same thing. Maybe not an 88 median, but I expect the class average to be solid. Yes, sir. I curve down. No. I usually, it's usually fair, right? It's usually fair. I don't need to do any adjustments. But I never curve down, though. That's,
Is this unusual?
Pardon me?
It's going to be here.
Yeah, it's going to be very, very, very. I think. We'll see. We'll see. Okay. Just study so that it goes good, and then that's it, right? So I actually tell you, I did maybe once I had to curve up, and this curve was like 1%, 1 or 2%. It's not a. I've never had to curve up by or adjust the grades. I think it's usually at a good level. Great. So let's try to draw these. I mean, what's the point of making it hard so that you curve up? Well, I never understood that point, right? There are maybe, I don't know. Just make it fair, and then everybody will get a good grade, or the grade they deserve. But as you see, the class is not easy, right?
Yeah.
It's not an easy class. So you work hard, you'll get rewarded. You don't work hard, then good luck. You know what that means. Let's do this. This is a question that you can get, for example. That's a nice question. You can get these types of questions. So let's try it. Oh man, gotta make sure to not. Yeah, okay, that's fine. That's fine. That's fine. So I mean, we've got a bad surface here. So what do we have to do? We have to sketch. Let's sketch this. Here I may need water. X. Well, I mean, let me Z and Y. Okay? Or let me put the X here, actually. Let's put the X here. I think maybe easier. I mean, anyway, you can represent it, but how do I sketch this? How do I try to sketch this? So I have Z is x squared minus 1, and then you're translating it for all the values of y, right? You're just Z is equal to x squared minus 1 in the xy plane, in the zx plane, right? Just draw Z is equal to x squared minus 1 in the zx plane, and or in maybe the first option, if you let's say, no, I don't need the first option. I want to really see the book. No, that's okay. No, it's actually not in the first option, that's it. Okay? Great. Now, do you see how to draw this? Z is equal to x squared minus 1. Do you know how to draw it in the zx plane? If I tell you the zx plane, can you draw Z is equal to x squared minus 1? Yeah. So what do? You just this is the zx plane, and you do it for every value of y. That's what's happening, right? Z is equal to x squared minus 1. This is my zx plane here. I drew the parabola, and then I just go back. And this can be easily done by papers. Right? Z is equal to x squared minus 1. It looks like something like that. Everybody. That's what you do. Right? And Z is equal to x squared plus 1. It looks, 1 minus x squared. It looks something like this. Right? Now, where do these two intersect? At what level of Z? Z is equal to 1 minus x squared is equal to x squared minus 1. So you take 2x squared is equal to 2. And Z is equal to 1, right? So I mean, the intercept, it goes like that actually. Right? Oh man. Anyway, this is how it goes, right? It's two parabolas that you're together, this tube, and I tell you, find the volume of this tube. Right? Provided that y is between 0 and e. Is it clear? Great. Now, where does Z range? What is the top and what is the bottom in that case? What is greater? I mean, draw it in the zx plane. 1 minus x squared is the top, and x squared minus 1. X squared minus 1. Wait, is it 1 minus x squared? Yeah, so wait a second. 1 minus x squared is equal to 2. No, they actually intersect that. minus 1, and z, the height is 0, right? Z is 0, sorry about that. I said z is equal to 1, right? Is that what I said before? So z is 0, that's when they intersect. Right? They intersect at height 0, and you're just taking the volume of this thing that you get. So that's like an egg, right? You have an egg, and then you're doing it this way, and you take the volume between y equals 0 and y is equal to 2. So that should be clear here. What's this integral? Where does z range? From x squared minus 1 to 1 minus x squared. Where does y range? 0 to 2, right? And you say where x ranges? Minus 1 to 1, right? dz, dy, dx. I mean, so you don't have any y here, right? If you don't have any y, you can integrate y, so you can integrate 2, right? And then you just have an integral on z, minus 1, 1, x squared minus 1, 1 minus x squared, dz dx. This is easy. Now you get 2. 1 minus x squared, so you get 2, integral from minus 1 to 1, 2 minus 2x squared, dx. So you get integrate 2, so you have 2 times 4. X cubed from 1 to 0 is 1/3, so it's minus 2/3, so times 4/3, is that it? We get this? Yeah. So you take out 2, so 1 minus x squared from 0 to 1. So it's 1 minus 1/3 times 2 times 2. Yeah. Okay? Great. Is it clear? That's a fair question, right? It's not that bad. Let's do more stuff. I mean, I think we're good with triple integrals. Are we? Or should we do more? No more? More or not? What do you guys want? No more? It's up to you. Yes? Now? Sure. I mean, let's try and do like one. Let's try to do some like one multiplier. Sure. Do you want to do this now, or what do you guys want to do? I mean, I can start a new thing, or I can leave it until tomorrow. So, like, one thing is not for final material, and the part of curves, the part that you're responsible of, is going to be very easy. Yeah. Okay, but it's going to be very easy. Okay, it's not going to be, the hard part is not going to be there. Okay, and you'll be surprised on how easy the question on the final is about this. Okay. For tomorrow's material. Tomorrow, yeah. Yes?
What does an x mean from the left end of the parabola to the right?
Ah, so you want x to range here? You could do that, but yeah, you may have to split it into 2. Right? So if z is negative, right? X will range, what is this curve? X will range from this to this, so what is it? Z is equal to x squared minus 1, right? X might range from square root or negative square root 1 plus, let's see, 1 plus z, right? 2 square root 1 plus z. This is if z is negative. And if z is positive, x will range, so this is z. And this is here. Z plus 1, right? And here x is equal to 1 minus z. So express z in terms of two functions of x.
Like either x is constant.
In that case, yeah. Just like in 2D integrals. Right? Now this is not nice because you have to split z. Like x doesn't vary between the same functions of z. So you have to write this integral in two different integrals. So one of them will be z from -1 to 0. X goes from here to here. Plus y goes from 0 to 2. The other one would be x goes from here to here. Z goes from 0 to 1. And y goes from 0 to 2. Okay? So it's always a good idea to try to simplify the integrals. I mean, we can try and do them actually. If you want, we can try and do them and show we get the same answer.
Yeah.
So the answer here, the first answer will be 4 minus 4/3. And the second one will be also 4 minus 4/3. Okay? You see that? So if z is negative, x will vary from this curve to this curve. If z is positive, x will vary from this curve to this curve. I mean, it's the same curve, but in branches. So you have to split your integral here. You have to say z goes from -1 to 0, and then x goes from here to here. And then if z goes from 0 to 1, x will go from here to here. Okay? Let's do a few more. I think now we're good. Okay, I think we're good for this. If you guys have questions on triple integrals, we've done enough examples. Again, questions like that you may get on the final. So please, things like this, be sure to master them. Okay? It's not going to be, I'm writing the final, so like, try not to look up for other exams or other things. It's better to stick to the course notes. I mean, the more the better, sure, but I'm pretty sure you feel the time is not, you feel that you don't have a lot of time. So I would advise you to review the notes and review the examples, okay? And then, should you do that, I think you'll be fine. And if you do that honestly, like just go and retry the examples. Don't look at your notes. Try them all. Don't say, so I can tell you what I used to do. I used to look at the notes and try the example, and then I failed. And then I look at notes, I say, oh yeah, that's how you do it. And so on, and so on, and so on, until you get, boom. You see on the final you don't know anything, although you are sure that you have seen almost every single example. So please try not to do this, okay? Try to rework every single example, even if it takes you 10, 15 minutes, that's fine. Okay? I think that's a good way to guarantee that you'll succeed. Great, okay. Well, I guess now we'll start a new thing. It's called surface area. We have 1 hour left. Now, in Math 264, you will see this in bigger details. Now, we're going to see that we're not going to motivate this a lot. You're not responsible for this for the final. I just forgot to put a question on this, right? It's not that I thought it's not done in Calculus 3, but apparently it's done. Not everybody does it, but in general it's done. Now, notice that you have a surface. Z is equal to fxy. Above a region R in the xy plane. Okay? for xy is r. Now a surface, how many dimensions does this have? A surface. This is my surface. How many dimensions? 2, right? A plane, how many dimensions does a plane have? 2 dimensions. A plane is 2 dimensions, right? How many vectors do you need to know a plane? You need 2 vectors that are non-parallel, right? A surface has 2 dimensions. So if something you have a 2 dimension is a 2-dimensional object, what can you talk about? So if you have something that is 1-dimensional, so a line, a curve, you can talk about the length of the curve, right? Now if you have an object that is 2-dimensional in 3D space, what can you talk about? The surface area, right? It's the area. Right? You guys see this? Here, the surface area of the surface Z is equal to fxy above the region, or above, I don't know what it's above, but there's a good phrase. It's not necessarily above. Let's see how to do that in a nicer way. Oops. Okay, so the surface area for xy and r is given by double integral over r square root of 1 plus fx y provided fx and y are continuous. It's a very easy formula. Let's do an application. Find the area of the part of Z is equal to x squared plus y squared that lies under the plane Z is equal to 4. I mean, really, it's really easy. Let's do this here. If the parabola is Z is equal to x squared plus y squared, and it's cut by the plane Z is equal to 4, and the intersection of these two surfaces is a circle of radius 4 at height of radius 2, at height 4. So, what is the part of the surface, guys, please? What is the part of the surface that lies below the plane? How can you describe x and y? Where do x and y range? They range in the disk of radius 2 centered at 0, right? This surface area is, so let's look at the formula. So it's double integral over x squared plus y squared, that's equal to 2. What's the square root of 1? What is the derivative of z with respect to x in that case? 2x, so it's plus 2x squared plus 2 r is from 0 is 1 here, from 0 to 2, square root of 1 plus 4 r squared, the Jacobian r dr theta, then it's 2 pi, this you can easily integrate, right? You can integrate this easily, right? You see that? How to integrate this? So it's 1 plus 4 r squared to the 3 halves divided by 3 halves. I have r derivative of 8r, so it can multiply by 8 from r equal to 2 to 0. So it's 2 pi 17 to the 3 halves over, okay? 17 to the 3 halves, yeah. No, 4 halves, 4, yeah. 17 to the 3 halves divided by 4. Yeah. Okay? Oh shoot, I forgot something, right? Minus 1 over 12. Okay, you can cancel the 12, put 5 over 6 times 17 to the 3 halves minus 1. Okay? Really, just a double integral. This is just a double integral. Good thing you don't have to know it. 264 is more of this type of stuff. Okay, great. So enough with integrals. Now we're going to start a new chapter. Curves in three-dimensional spaces. Okay, so I'll write this one. So surface area, please note that it's not covered on the exam, but there are 2 or 3 workbook questions on it, right? Yeah, so I think it's not that bad. We just have to do this. Great. Questions? You probably don't care about this, but that's fine. So let's go back to Calc 2 a bit. Calc 2, did you see the length of the curve y is equal f of x? Right, did you see that? From the square root of 1 plus f prime of x squared, right? Great. Now the goal of this, Calc 2, get a curve y is equal f of x. And what did you say about the length? It's the integral from a to b of the square root of 1. You remember this? Did you see this? Did I mess up the formula? I hope not. I don't think so. That's what you saw, right? Now, in Calc 3, we're going to generalize this. Into curves in space. Okay? Of course, we're going to do a bit more. Today and tomorrow, we're going to do a bit more than that. Okay, now let's see. Are we all? Yes, sir. Yes. This is covered. This is covered. You may have something, you will have something easy on it, so you could have an easy proof on this thing. Yeah, you could have a proof, but it's very easy. We're going to see some easy proofs. Okay, just a easy thing and quick. I mean, if you notice them, then quick. Okay, so yes, sir.
They will more likely be free response or
You'll see. Okay. Could be easy, right? That there's but you'll have one question. You're not going to have more than one question. Could be a long answer. Could be a proof, and the long answer could be a multiple choice. Okay, great. Okay, before we begin, are we all comfortable with dot products? Are we comfortable with cross products? Great. So if I have two vectors that are parallel to each other, what is the cross product of these two vectors? 0, right? So the cross product of a vector by itself is 0. Great. If I have two vectors that are orthogonal to each other, what is their dot product? 0. Very good. And if I have a cross product, if I have two non-parallel vectors and I have a cross product of them, what does it do? It gives me a third vector. That is perpendicular to the span of the two others, right? Is that what you saw? Great, awesome. So we're going to use this. We're going to do some calculus now, but with cross products and vector products and every single, vector. Well, not every single, but vector operations that you have seen. Okay, so space curves. Be continuous. Constants on an interval I. The set of all points x, y, and z in R2 such x is equal to f of t, y is equal to g of t, and z is equal to h of t. As t is in I, it's called a curve. Example, if you take x is equal to minus 1 plus t, y is equal to 3 plus 2t, and z is equal to 17 plus 8t, what do these represent? These represent what's the equation, the parametric equations of a line, right? Represent the line passing through minus 1, 3, 17 to the point minus 1, 3, 17 and parallel to the vector V. What is a vector that is parallel to this line? Can you extract it? 1, 2, 8, great. Okay? Yes, sir.
That is called a parameter.
Parameter, yeah, exactly. Okay? Is that clear? So I have x, y, and z. There are functions of a single parameter t. Okay, so RT we call RT, which is f of t, g of t, h of t, and the position method. Okay? Right? Yeah? That's what we call the position vector. So at time t, basically, it gives you 1 point. At time t1, it gives you another point. At time t2, it gives you a third point. So far, so good? Very easy. Great. Let's do examples. Curves in the plane z equals to 0. you give me a t, and you give me 1, and I give you f of 1. You give me 2, and the y value is f of 2. How can you trace this curve? This is just the curve y is equal to f of x from x is equal a to x equal b, right? Do you agree that this is this curve? Yeah? You see that? 1, what's the position of R1? R1 is 1 over A, f of A, B, f of B. Something here times f of that something. Right? This is R of t. Is that clear? Great. Now what's another way? Well, are there curves that cannot be represented as a function? So if you take the circle, can you represent it as a function? Y is a function of x? No. But how can you parameterize the circle? So if I take R of t is equal to cos t and sin t. T is between 0 and 2 pi. What do I get here? Do you agree that I get the circle of radius 1? Do you guys see this? If t ranges from 0 to 2 pi, cos t sin t, what does it represent? It represents the point on the unit circle. You see that or not? You guys see this? Cos squared plus sin squared is equal to 1. The unit circle is x squared plus y squared is equal to 1. Right? This is the unit circle. And a point here is given by cos t. Well, so what is r of 1/2 basically, or r of pi over 3, let's say? It's cos pi over 3 sin pi over 3 1/2 root 2 over 2. Right? What is t in that case? T is my angle, right? This is t in that case. Right? This is the parameter. Awesome. So far so good? Easy to score. Let's see if we could do. Derivatives of the position vector. Okay. Now if I have R of t, so let's say I have a curve here. Well, this is a bad curve. I have a curve in 3D space, and the position here, this is RT0, let's say, and this is RT0 by sine RT0 plus h. And I draw this. Okay? I have 2 points. RT0 is a point, RT0 plus h is another point. Now, look at, if I draw the line between these two things, what is the slope of this line? Delta. What is the slope? Well, there's no slope here, but because you're in 3D. But how do you expect this? How do you expect the change in position to be? What is the change in position? What is the change in position? You can write it as RT0 plus h. Minus RT0, and how much time passed? H. Great. Now as h goes to 0, what happens to this secant line? It becomes a tangent, right? So as h goes to 0, this line becomes tangent. So how do I describe this as h goes to 0? by a, by what? By a limit, right? H goes to 0. Great. Now let's write the difference in position. Over H. Now, when I distribute the limit inside, what do I get here? I get here f prime T0, g prime T0, and h prime T0, provided f, g, and h are differentiable at T0. Right or no? Great. So how do I define the derivative vector of RT? The derivative of RT, how do I define it? Or I mean, it's a pointwise operation really. We define R prime of T to be just equal to F prime of T, G prime of T, and H prime of T, provided X, G, and H are okay. Here you don't have to worry whether or on this side. Anyway, okay. Now, what's the tangent vector to the curve RT to the tangent vector? At the point what is the tangent vector to the curve RT at the point where t is equal to T0? This is just, what do you expect it to look at there? What's the tangent vector? S prime T0, G prime T0, H prime T0, which is R prime to 0. Okay? Great. Let's do an example. Find a tangent vector to the curve RT, let's say close to sin t and t, at the point where t is equal to 1/2. What is this? How do I find this? First of all, what do I need to do? I need to differentiate R. What is R prime of t? It is minus sin t cos t and 1. A tangent vector to the curve RT at the point where t is equal to 1/2 is tangent vector to RT at the point where t is equal to 1/2. What is that? This is just R prime of 1/2. It's minus sin of 1/2 cos 1/2. I picked the best one for 3. Okay? Yeah? Great. Let's do one more thing. Let's try to recover what you know from calculus 1. Calculus 1. So I have the curve y is equal f of x. What is the equation of the tangent line at the point A f of A? It's y is f prime A times x minus A plus x of A. Tangent line to y equal f of x The slope of the line is f prime of a, right? So what's the tangent vector for this curve at this point is 1 f prime of a. Do you agree? So a tangent vector for this curve is hence 1 f prime of a at a f of a is what do we call it? Let's call it b. Okay. 1 f prime of a. Let's try to recover this by the means of cos3, by the methods of cos3. So how can I parameterize y is equal f of x? You give me x and then you give me f of x. So I take f of x f of x, and I'm looking at the tangent at the point where x is equal to, when is x a f of a, when is our x a f of a? It's when x is equal to a. So what do I have to do here? I differentiate r prime of x, what is that? It's just 1 f prime of x, right? And what's the tangent vector when x is equal to a? It's 1 f prime of a. Okay? We obtain this again. We do one more example. Should we do one more? Yes. The curve is hence. No, what? I can't even. Yeah, it's hence. What? A tangent vector to the curve is hence at a f of a is hence these vectors. Okay. Let's do one more. Let's take the circle. The unit circle. Now you know sometimes when you try to, well anyway, let's try the unit circle. The tangent at this point, what vector do you expect to be tangent at this point? At the point on top? What the tangent you expect it to be horizontal, right? And at this point you expect it to be vertical. That's tricky. So I parameterize the circle. RT is cos t sine t. Great. What is r prime of t? R prime of t is minus sine t cos t, right? Now at the point on top, what is the value of t that gives me the point on top? The point on top is 0, 1, right? What is the value of this gives me the point 0, 1? Pi over 2, right? R prime of pi over 2. This is minus 1, 0, right? Look at this. It's going in this direction. And at this point, which is the point 1, 0, what value of t gives me the point 1, 0? T is equal to 0. R prime of 0 is 0, 1. Look at this. This is the tangent vector. Okay? You see that? You see that? Okay, great. I mean, you don't have to see these as points. You have to see these as vectors. Right? 0, 1. The vector 0, 1 is not fixed. A vector is, a vector you can put it everywhere. Right? Great. Okay. Now let us do some derivatives. Okay, so suppose u of t is at 1 t, at 2 t. How much time do we have left? 3 t? 10 minutes? 30. That's good. I think we're going to get suppose that u of t plus v of suppose u of t is this and v of t is this, where f1, f2, f3, g1, g2, g3 are differential. How do we define the addition of two vectors? U of t, what is u of t equal to? U of u plus v of t, what is that equal to? This is just f1 of t plus g1 of t, f2 of t plus g2 of t, and then f3 of t plus g3 of t. What is d by dt of ut plus vt? What is that? It's clear, right? This is just f1 prime of t, g1 prime of t, f2 prime of t, plus g2 prime of t, and then 3 prime of t, plus g prime of t. And this is nothing but just d by dt u of t plus d by dt. Okay? So really, when you add two vectors and you differentiate, you can just differentiate each one separately and add them. Okay? Yeah? Is it clear? This is just the regular law, the regular addition rule. And let's do one more. If t is constant, what is d by dt of t u of t? What do you expect it to be? Multiply the c by all by f1, f2, f3. Do you expect, and how does the derivative of t, what is the derivative of t f1? Is t f1 prime, right? So then it's clear? I call them f1, f2, f3. So let f of t, let f be differentiable. Then d by dt, f of t times ut, which is just the vector. So you multiply the vector ut by this number. F of t gives you a number, it's a real valued function. Okay, so d by dt f of t is just, you multiply f of t by each of these three components, and then what do you get? What do you get here? This is equal to what? To f prime of t, f1 of t, plus f1 prime of t, f of t, you agree? Do the same thing, f prime of t, f2 t, plus f2 prime t, ft, and then you get f prime t, f3 t, plus f3 prime t, f of t. Let's write this in a nicer way. Okay, let me add them. I don't know if this. Okay, now let's take an f prime t out. If I take an f prime t out, what am I left with? I'm just left with f1, f2, f3, which is just u of t. And then I can take an f of t out. And now I'm left with u prime of t. This is d I dt f of t. Okay, these you can memorize, or I can ask you to remove them. Okay? Great. Now these are fairly standard, right? Because it's all how regular products of functions behave, right? What's the product? I'm just applying it 3 times and doing a vector operation, adding and multiplying. Great. But now we're going to move on to an operation that is proper, or that is at least interesting for vectors. Now d by dt of ut dot bt. So I have 3 vectors and I take their dot product. What can I say about their derivative? And the answer to that is you also have a product rule here. So this is just ut dot b prime t plus u prime t dot bt. Should I show this or not? Should I show this one? I show this one, and I will leave the other one as an exercise. But you should do them, okay? Okay? Proof? Oh man, it's gonna be bad, but let's do it. What's ut dot bt? I mean, you know, let's treat them as functions. So that we make annotation a bit easier. U dot b, this is just f1 g1 plus f2 g2 plus f3 g3. So ub prime, what is that equal to? This is just f1 prime g1 plus g1 prime f1 plus f2 prime g2 plus g2 prime f2 plus f3 prime g3 plus g3 prime f3. What can I do here? I just want to take I want to take u and b prime. So where is my u? Where is my u? Do you guys have to regroup them? So write it this way: f1 prime g1 plus f2 prime g2 plus f3 prime g3 plus g1 prime f1 plus g2 prime g2 plus g3 prime f3. What is that equal to? This is just f1 prime f2 prime f3 prime dot g1, g2, g3 plus g1 prime, g2 prime, g3 prime dot f1, f2, f3 What is that equal to? It's just equal to u prime dot b plus b prime. Okay, great. These are the operations of this. So scalar product really can behave as a product rule, but for vectors, for like vector functions of one parameter. Now we have one more, This one is left as an exercise, and I encourage you to do it. Okay, I encourage you to do it. Show that d by dt is cross product, right? Is equal. If you pay attention, it's u prime v plus u v prime. Okay? It's a nice example, nice exercise of manipulating derivatives. Yes, sir.
You don't mind if they don't try the arrow?
Pardon me?
You don't mind if they don't try the arrow?
That's fine. You can write an arrow, or you can keep it this. You prefer to write arrows? I think it's now it's too late, I guess. But okay. Awesome. Okay, so please do this exercise. It's a nice exercise.
We should know this book, right?
Pardon me?
We should know this book.
Yes. You should know these proofs. These proofs, you should know them. I can ask you, for example, do this that you didn't do, or I can ask you to reproduce one of them. Okay, yes, sir.
Does this one want even with the point?
Everything. Like these are easy things, right? These are just derivatives. So it should be, if you have something like that, it should be 3 marks. Okay, these are just derivatives of one dimension, combined with some addition of 2, 3 vectors. Great. Now. Now move on to interesting things. So, do you remember how you do the length of a curve in Calc 2? You remember how you derive this? You decompose it into small right-angled triangles, right? You remember this? So this is the motivation behind this. So length of the curve y is equal to f of x, from x is equal to a and x is equal to b. So what you did here is that you decompose that, and you decompose it into things, and then you went like you approximated it by the line segment, right? Is that what you did? You remember this? This is how you approximated it. You took the oh man. You remember this? Okay, these will get that. You remember this idea? You did this, right? You remember that or not? Yeah? So really, and then you use that to find the length. Right? You guys remember this? This is how we do this, right? Now, a very similar argument for a curve RT. Is that the length of RT between the points C and B is Okay. I mean, let's try to recover the result here. Let's try to recover this result. Here, what can I parameterize my curve? I can parameterize my curve by R of t is equal to t, f of t, and t between a and b. dt by dt is equal to what? dt by dt. Let's look at the formula there. So my x is t, right? X is t. X is equal to t. Y is equal to f of t. dx by dt is equal to what? What is dx by dt? 1. What is dy by dt? F prime of t, right? What is the norm of r prime of t? Is the square root of 1. Okay? And you get the same argument, the same result. Okay, this is a bit more general. Okay, enough said. Let's do more examples. Let's do some examples with numbers now. Arc length. So I mean, this used to be seen in calculus 2. You didn't see this in calculus 2. At least in dx, dt, dy, at least in without a z. Did you see this without a z? Without a z. So dx, dt plus dy, dt, did you see that? Oh, okay, that's nice. Okay, everything looks familiar. Okay, that's good. Okay, we should do an example. Let's do an example. Find the length of t3 equals t3 times t. Let's say from t between 0 to pi over 4. What do I have to do? I take our prime of t. What is our prime of t? Can you help me? Our prime of t is what? 1 minus 3 times t. 3 equals times t. What is the norm of our prime of t? This is the square root of 1 plus 9 times squared t plus 9 whole squared t, which is just square root of 10. So the length is 0 pi over 4 square root of 10 dt. What is that? It's just pi over 4 times square root of 10. Yeah? Great. Let's so did you see arc length? Did you see the arc length function? The integral from I don't know a to t r prime of x dx. Did you see that? Man, okay, didn't see that. Okay. Okay, So in Calc 2, have you seen that a parametrization is not necessarily unique, right? You can parameterize the curve in two different ways, right? Did you see that or not? You didn't see that? No, you didn't see that? So if let's pick an example. Let's pick what does this parameterize? This parameterizes a line, right? Passing through the point -1, -1, -1, and parallel to the vector 4, 6, 8. You agree or not? Now let me parameterize perhaps a different line, but let's see, it's really not the same. It's really the same line. Okay, so the S is fine. I mean, you know, that's so if I use the line -1 plus 2s, -1 plus 6s, -1 plus 4s, is it 3s? Sorry. Is it the same as the previous line or not? That's the same, right? You see that? So really, I parameterize s by t over 2. Right? Now, pardon? Yeah? So s by t over 2. You can put anything you want here. Well, technically, depends. But depends if you want to target all the segments or one segment or whatever. But you know, s of t over 2 will recover exactly the same line. Now we will show, I think, in calculus 4 that the length does not depend on the way you parameterize, which makes sense, right? You agree? I mean, parameterizing basically, if I go from here to here, or I parameterize differently, I go from here to here. Is it the same length or not? Does it depend on the way I travel? No. Okay. So you will see that in Calc 4 that the length is independent of the parameterization. Okay. Now let's introduce the arc length function. Suppose our P I don't know if you've used this notation before, but you can write it this way. Have you seen this notation before? The curve. Where? R prime. Continuous. Just let me check something if they have that. Okay, there's something. Okay. Arc length function. Is S of t R prime of u du. Okay, so the arc length function, if you have a curve, from A to B, from T is equal to A, this is the point R of A, and this is the point R of B, and this is the point R of B. The arc length function is just the distance, is the length of the curve from A to T. Okay, this is the arc length function. You integrate from A to T, R prime of u, the norm of R prime of u du. I think you saw this in calculus 2 for two variables, right? Doesn't matter. This is the arc length function. So you just cut the length from T equals A, from A to the point T. You fix T, that is bigger than A, and less than B, and you look at the length from R of A to R of B. Now here you must see that the curve T is not overly parameterized, right? You don't parameterize it twice. You just go one turn, okay? But you don't have to worry about that. Okay, great. Now, what is S prime of T? By the fundamental theorem of calculus, S prime of T is equal to what? Fundamental theorem of calculus, S prime of T is equal to R prime of T. Okay, enough said. Let's do an example. Find S of T as R of T equals to sin t, okay? Measure from the point where t is equal to 0. So what is S of T in this case? S of T will be the integral from 0 to T, the norm of R prime of u du. What is R prime of T? R prime of T is minus sin t equals to Tn1. Norm of R prime of T is square root of sin squared plus cos squared plus 1. So the arc length here, R prime of u, the norm of R prime of u is just root 2. And this is just d. Okay. Have you seen parameterization by arc length or not? Have you seen that? No? Okay, great. Let's do that now. Suppose R of T is a curve. And let S of T, let's say ATB. And let S of T is on 0, T from A to T, the norm R prime to du, be the arc length function. What is ds by dt? By the fundamental theorem of calculus, ds by dt is just R prime of T, the norm of R prime of T. And hence, dt by ds is 1 over R prime C, provided R prime C is on C. Okay? This is, you should know this. You can know them by heart, or you can just redirect that. That's fine. Okay, now let's recall that. Yes, sir. Am I going a bit fast or not? Is it fast? Okay. Great. How much time do I have left? 0. Oh, okay. Great. So we'll continue tomorrow. Okay. Yeah. If you guys have questions, yes. Parameterization.